In this video, we'll cover how to calculate free energy in non-standard condition. I like to start off with an equation here. Delta G is equal to delta G naught plus RT ln of Q. The delta G naught here represents what we have learned so far, which is the free energy change at standard condition. But remember, we're trying to look for a position where it's a non-standard condition. And let's see, the R is the gas constant, 8.314 joules per Kelvin per mole. And we have temperature in Kelvin, and we have this Q. I don't know if you recall, this is the reaction quotient, and it stems from when we got the when we got the product over the reactant, and then we had the exponent as part of its coefficient in a balanced equation right here, the x, y, m, and n. So this equation is used when it's non-standard conditions. So it's not 25 degrees, it's not at 1 atm, it's at a total different number. And so at equilibrium, we can utilize the same equation but sort of manipulate it by making delta G equal 0, because the free energy is 0 in non-standard condition when it's at equilibrium. So if I rearrange this particular equation to here, that delta G was 0, so I put the delta G naught on the other side and made negative RT ln of K. So this is again the free energy change at STP, standard condition, and pressure, temperature and pressure, and you got your R, you got your T, and then now instead of a Q, you have a K. What is K? It's that reaction quotient. It's the same thing, but it's at equilibrium. You might have a different concentration value, but that's all, but it's stemming from the same, the reaction quotient. So these are a lot of terminologies that I have brought to you and equations. So let's try a learning check. In this learning check, we'll have, we want to know the free energy change for the process shown here under specified condition. And though it might be at 25 degrees Celsius, thinking that it is standard, it is not standard because if you look at the partial pressure of all of these guys, they don't equate to 0, nor are they 1 themselves. I'm sorry, they do not equate to 1, nor are they at 1 atm themselves. And so we're going to go ahead and assume that this is not at standard condition. And if it was standard condition, I think I would write what is the standard energy change. Also, to note that this is not at equilibrium, you notice that the arrow is going towards the right. You don't see a double arrow going back and forth, and that means it's not at equilibrium. So we're going to go ahead and write out the equation of the delta G in non-standard condition and see what's missing and start to plug in some values here. Q. Delta G naught is already given to you, which is 33 kilojoules per mole. But notice that this is a kilojoules per mole. Well, you're eventually going to need to convert this either into joules, or this side needs to be in kilojoules. That's because the R, gas constant, is in joules per mole per Kelvin. So to make things easier, I'm going to go ahead and put this into joules. So how do I do that? It's 33.0 kilojoules per mole. You're going to take every 1 kilojoules. You know, there are 10 to the third joules. So therefore, that is 33,000 kilojoules. Oh, not kilojoules, joules. So there's my joules. And also per mole, don't forget the moles, per mole. So I'm going to come back here. This would be 33,000 joules per mole. Okay, what's R? Well, R, we know it's given 8.314 joules per mole dot K. What's temperature? Well, the temperature is given over here, but it's in Celsius. So if I were to convert this into Kelvin, we'll need to add it to the 273.15. And if you do that, you would get 298.15 Kelvin. So let's go ahead and plug this in, 298.15 Kelvin. What about Q, right? ln of Q. There are a few factors that you'll have to look at. Well, these are all gas, so which means that all of the component is there. Remember, it's the product divided by the reactant with the coefficient being the exponent. So we know H2, that's my hydrogen gas, is 0.250. So that's 0.250 to the third power, since the coefficient is 3 in the balance equation here. Then we have our nitrogen, which is 0.870, and it's to the 1 power all over. And then we have our ammonia, which is 12.9. And then we need to put that to the second power. All right, so try to calculate this on your own and see what you come up with, and then come back, and I'll show you in the calculator too. So I want to take care of whatever is on the right side of this portion over here. This portion, okay? And then I'll add it to the 33,000 since it looks much complex here. So let's start up with the ln, okay? So we have the 0.250 to the third power. And let's parenthesize this. Multiply by 0.870. And then I'm going to divide this by 12.9 to the second power. So hit enter, divided by 12.9 to the second power. There we go. So that's the value I get, and that's inside of this ln. So we have to incorporate the ln in, ln second answer, and that's what I get. So I get a negative value. Now I will get multiplied by the temperature and the gas constant. So first the temperature, 298, working backwards here, times 8.314, okay? And added to the 33,000. And I get 9,667. And let's keep this as it should have been at 3 sig figs. Okay, most likely I will ask you to specify how many sig figs. I'll say, hey, put it in 3 or 4. So if I were to put this in 3 sig figs, it would be 9,670. And what's the unit? It's joules per mole. All right, let's do a next learning check. Here it says, given the standard free energy of formation of silver plus and chloride minus with and silver chloride solid are 77.1 kilojoules per mole, negative 131.2 kilojoules per mole, and negative 109.8 kilojoules per mole, respectively, calculate the solubility product with KSP. It's looking for the KSP for silver. Temperature is at 25 degrees Celsius. So it's asking for what is the equilibrium constant, right? The KSP. So it's at equilibrium. You can already tell by here, that double arrow, okay? So let's go ahead and write out the equilibrium equation. delta G naught is equal to negative RT ln of K. And the K is what they're asking for. Okay, that's what they want to know. Well, we have delta G? If you look over here, you don't have the delta G naught, but we do have the value for the standard free energy formation of so individual G naught for these guys. And remember that delta G naught is equal to the summation of the coefficient of the product. So my product here would be silver and plus the summation with the coefficient of chlorine. Okay. And then we would get, hold on a sec. I'm writing concentration here, not concentration. I meant G. G's for silver, and then G for chlorine ion, silver ion. And then you're going to subtract that, okay, all of this, subtract, and then with the summation, well, there's no really summation because of reactant, there's only one with the coefficient silver chloride. Keep doing that. Delta G of silver chloride. Okay, now we can go ahead. Not delta G, just G. Now we can go ahead and plug in some values here, and it says for the free energy of formation for silver, silver ion is 77.1 kilojoules. So let's go ahead and plug that in. So every 1 mole, how did I get 1 mole? Because you look at the coefficient of the balance equation multiplied by the 7.1 kilojoules per mole, right? That's for silver, plus now for the chlorine ion, that's 1 mole multiplied by negative 131.2 kilojoules per mole. Okay, and then this is summation, so you need to add these two together before you subtract it with the reactant, which is 1 mole. For silver chloride, it is negative 109.8 kilojoules per mole. Okay, so go ahead and try calculating this out and then come back and check the key. So coming back, hopefully you got 55.7 kilojoules. So we want to convert this 55.7 kilojoules into joules. So we're going to multiply this by 1,000 pretty much. So 10 to the third joules is all over 1 kilojoules. So kilojoules cancels out and you get 55,700 joules. So that's how much delta G is. So we know delta G right here. Do we know R? Yes, that's the gas constant. Do we know T? T temperature is at 25 degrees, and then we can add 25 plus the 273.15 to get it into Kelvin, which will give you 298.15 Kelvin. So we can plug that in, and then we can get K. Now I want to rearrange this equation before I start plugging in. So I'm going to divide this by negative RT both sides, RT. So that we just have ln of K is equal to delta G naught all over negative RT. So let's now plug in some of the values. So let me rewrite this up here. And that would be 55,700 joules I don't know why that's kilojoules over there. Joules all over negative 8.314 joules per mole dot K. And then you multiply by the temperature, which is 298.15 Kelvin. Okay, and that will give me ln of K. So if you were to calculate on this side of the equation, try that and then come back just on that left side. Should get negative 22.5. So now how do I get rid of ln? To get rid of ln, you do, so if you look in your calculator, there should be an anti-log, or I'm sorry, not anti-log, anti-ln. So it will be the ease of something. So there is a ease of, this E, and that will cancel out the ln. Now, where is this E, okay, on your calculator? So I will show you in mine. So the E is right here. So so you see the ln, and you should see ease of x on yours, okay, where the ln is. So you need to second ln, okay, then you get an E. Then you press negative 22.5, and that should give you the value, which is 1.69 times 10 to the negative 10, which is fairly, really small equilibrium, 1.69. That would be my K value.